I want to talk to you about something today that I think you probably already know, or at least have heard about, something that you're familiar with. Now, this is a topic that we may have talked about in QBA 237, Basic Business Statistics, but I know that it is something that you'll be familiar with. I just want to start with a discussion about what it means to be in a relationship. If you're in a relationship with another person, the way that you know that you're in a relationship is that when things change for you, the other person has a predictable response to that. So here's what I mean. If you're having a really bad day, your friend, your partner, your spouse, the person you're in a relationship with, kind of intuit that. And so if you're having a bad day, they're going to respond in a certain way. Maybe they'll do something to make you feel better. And if you're having a really great day, that person might respond to encourage you in that. And of course, if something happens with them, you'll be responsive to changes in them as well. It's that back and forth, that reciprocity. That's how you know you're in a relationship. On the other hand, if you say that you're in a relationship, but when you're having a great day, the other person doesn't really notice or care, and if you're having a bad day or you need something, a ride to the airport or just money for food, that person doesn't respond anyway, my friend, you're not in a relationship. Maybe it's imaginary, maybe you're a stalker. Either way, no relationship exists there because changes with you don't correspond to any changes with them. What I want to talk about, though, is relationships between variables. And this is a topic about correlation. What would it mean for variables to be in relationship? Well, here's what it would mean. If two variables are related, then changes in one variable are consistently associated with changes in the other variable. Correlation, it's right there in the name, relationship. We're talking about relationships between variables. So let's make this make a little more sense by talking about an example where we are running a concession stand for the football game. And we're going to have two variables in play. The first one is temperature. And temperature is going to change across the season. Early in the season, and when it's August, it's going to be really hot. Temperatures will be in the 90s. But as the season goes on, as we get into October and November, the temperatures are going to drop. So at any given game, we'll have a certain temperature outside. And our second variable is going to be sales. We're interested in what happens to sales in response to temperature. Like for instance, as temperature goes up, as it's really hot outside, what happens to our sales of cold soda? When the temperature is high, we're going to sell a lot of cold soda. But as the temperature drops, as it gets down into the 30s and 40s, the sales of cold soda is also going to decrease. We're going to see those two moving together. But as the temperature increases, what is going to happen to the sales of hot chocolate? If it's August and it's 95 degrees, we're not going to sell much hot chocolate. But as the weather gets brisk and everyone is bundled up and it's really cold, we're going to sell a lot more hot chocolate. There's an inverse relationship between those two variables. They'll move opposite of each other. What about the sales of those big foam #1 fingers that we also sell at the concession stand? What's going to happen to those sales? Well, probably temperature is not going to tell us very much about the sales of foam #1 fingers. That'll have more to do maybe with the fact of whether the team is winning or not, or maybe some other variable at play. Temperature won't tell us much about those sales. So what we see is three different possibilities. We could have variables moving together, we have variables moving opposite of each other, or we could have no relationship where information about one variable doesn't tell us really anything about the other variable. This is a bivariate scatter plot. Bivariate, that means two variables. When we're doing correlation, we'll use just two variables or two variables at a time. It is possible to do multivariate correlation where we have multiple variables at the same time. I'll show you an example of that. But for the most part, and certainly for this example, we're just going to be using two variables. Bivariate scatter plot. Well, what's that? The scatter plot graphically displays the direction and the strength of the correlation. We're going to start with two scale variables. Let's say height and weight. We're going to plot one of those variables on the x-axis, and we'll plot the other one on the y-axis. What we can then do is gather information from individuals, but we're going to need two data points. We're going to need to know your height and your weight. We're going to do that for everybody. We're going to gather a large amount of information. To plot this, what I would do is I'd go to my scatter plot. I'd look up your height along my x-axis. Wherever that falls, I would then move up the y-axis to find where your weight is, and I would put a dot at the confluence, the correspondence of those two numbers. So therefore, every dot on the scatter plot is actually representing two data points drawn from one individual. When you look at the scatter plot, what you're seeing are data points. Each data point is a pair of x and y scores, where n equals the number of pairs. Each individual is contributing 2 data points. If there are 20 people in our study, we have an n of 20, but there'll be 40 data points, except each one of them has to be paired up. We'll only end up with those 20 pairs. The regression line is that straight line that visualizes the relationship. And what I mean is that when we look at our scatter plot, when we look at this scatter plot, we see a line that runs through the middle of those dots. Not every dot is on the line. In fact, most of them are not on the line. But what we're interested in is how close are they to that line, the variability among all of those dots. Each of those dots is giving us some information that can be summarized in that straight line. So that straight line is called a regression line, and it works like a mean to summarize those data points so that we could eventually use this for making predictions. The scatter plot shows us the direction and the strength of the relationship between the variables. With direction, we really have two options, positive or negative. A positive relationship between two variables is when the variables move in the same direction. You remember our example with the cold soda and temperature. As temperature increases, cold soda sales increase. As temperature decreases, cold soda sales decrease. One variable increases, the other one increases, or as one decreases, the other decreases. Now, a way to think about that is look at the slope of the line. Start with positive. So imagine that you're beginning on the left end of the x-axis. If there is a positive relationship, as you move from left to right across the x-axis, you're walking uphill. You see that relationship? That slope, that direction of slope, that means there is a positive relationship between these two variables. On the other hand, if you start at the x-axis and you move along the x-axis from left to right, if you're walking downhill, that would be a negative relationship. A negative relationship exists when the variables move in opposite directions. One increases, the other decreases, like with the hot chocolate example. When the temperature is high, hot chocolate sales are low. As temperature drops, hot chocolate sales increase. We see them moving opposite of each other. The more you study, the fewer silly mistakes that you make. We see that negative downward slope and that negative relationship. The second thing that we can see in our scatter plot is the strength of the correlation. And for that, we're looking at how closely all of our dots align with that regression line. How close are they to the line? The strength of the correlation is the degree to which those scatter plot points form a straight line. In this example, we have a perfect negative correlation. And what do you see about the dots in the line? All of the dots are exactly on that line. It's a perfect correlation. Every x value is paired with one and only one y value. But that's also not realistic and really not that interesting. When you have a perfect correlation, it's boring, like night and day. If right now it's daytime, guess what it's going to be 12 hours from now? Nighttime. And 12 hours after that, it'll be daytime. It's a perfect correlation. It's boring. We don't learn anything from that. So what we're interested in is the types of relationships where they're not quite perfect. There's some variability in that relationship. And we're going to put the correlation strength and direction into a number called a coefficient, and that number is going to range between -1 and +1. The strength of the correlation is going to be dependent upon how close it is to either -1 or +1. Values of that coefficient that are close to 0 mean there's no relationship. But as they move in either direction, toward +1 or -1, the relationship grows stronger, and we'll see more of the dots more close to that line. When the correlation is strong, we see our dots lined up very close to the regression line. There's not a lot of variability. So in this first example with a positive correlation, it's a very strong positive correlation of a 0.91, you see most of those dots are either on the line or really close to the line. Anytime you use that line for prediction, you're going to have very little error in your prediction. So the points are close to a straight line, the variability is low, the relationship is strong. As the relationship weakens, the variability will increase, and you'll see that where we have dots that are further from the line. There is more variability in our model. We can still use our regression line for prediction, but we're going to have more error in our predictions because of the greater amount of variability in the model. But what if there is no relationship between the variables? Then what we'll see is just a cluster of dots. Let's say I want to predict your height based on your zip code. Does the zip code X variable predictor give me any information that helps in predicting your height? No. So if I plot zip codes against height, I'm going to get this cluster of dots. I could put a straight line anywhere through there. There's no one that's better than any other one. But notice where the line actually does end up. It's a horizontal line. What is that? Because this is about prediction, I want to predict a y value from my x value. And if there's no relationship, if zip code doesn't tell me anything about height, then if I pick an individual at random from this zip code, tell you the person's zip code, how tall are they? Your best guess is going to be the mean of y, the average height. If there's no relationship between the variables, if x doesn't tell you anything about y, then you can't use that x value for any predictive reason. You might as well just use the mean, the average height. That's going to be your best guess. So what I'm describing to you is the zero-order correlation between two variables. If I'm plotting blood pressure and BMI, the zero-order correlation is the amount of variability in one variable that is shared by the other variable. It's expressed in this Venn diagram as the amount of overlap. Here we see a moderate amount of overlap. If we wanted to depict something where there was a super strong relationship, maybe we have almost a complete overlap of those two circles. Regardless, it's that space in between of the amount of overlap that is the shared variability. Now, we can quantify this most easily in something called covariance, which is the ratio of the amount that x and y vary together versus how much they vary separately. So going back to our example with you and your best friend, you're in a relationship, you're buddies, you're close. You're probably more alike than you are different. So when I ask you about something that you like, I could probably predict that your friend would also like that same thing. But there's not 100% correspondence, there's some differences, but you're more alike than you are different, you vary together. The ratio of how much you're varying together versus how much you vary separately is called covariance. So if you have high covariance in a relationship, it means the two of you are really close. You have a strong relationship. There's a lot of overlap. The problem with covariance, though, is it tends to be a really big number, and it's dependent upon the scales that we're using for measurement. So if we're predicting like sales, which can run into hundreds or thousands of dollars, we might have a covariance that is just huge, and it doesn't help us with comparisons. What we're going to do is we're going to take that covariance and we're going to standardize it so that we can do comparisons. That's what correlation is, the standardized covariance between these variables. It allows us to make comparisons. I can show you a correlation coefficient of a negative 0.3, and it doesn't matter what the scale is or what is being measured. You know that is a weaker relationship than a negative 0.6. You can compare between correlations, the amount of overlap, the shared variance, by knowing the standardized covariance, which is what we call the correlation. Let's take a look at the correlation coefficient, the number that we use to depict numerically the relationship between the variables. The first thing that you'll note is that it is called R. Now remember, this is a correlation. Why not C? Well, we don't call it C, we call it R. And you might wonder, or maybe not, what does that R stand for? Well, I'll tell you because you might want to know. This would be a great test question, I think. Talk about predictions. It's important to know what R means in a correlation. The first obvious answer would be relationship. That's what we started talking about. But the R does not stand for relationship. The R in correlation means regression. It's that regression line. So you now know, when you see that question in the future, the R in correlation means regression. You see here, it's R sub xy. That means it's the correlation between variables x and y. If we only have two variables, we don't really need that x and y. We know it's x and y. However, if we were correlating, let's say, three variables, we would have R sub xy, R sub xz, and R sub yz. If we have more than two variables, it's a good idea to use that subtext in order to indicate which correlation we're talking about. The next thing you see with a correlation coefficient is the sign. That sign will either be positive or negative. If it is positive, that means you have a positive relationship between these variables. And if it is negative, it means you have a negative relationship between these variables. There's very few always and nevers in statistics, but this is one of them. Positive correlation coefficient is always a positive relationship, and negative correlation coefficient, always a negative relationship. And what is left with that number, we're interested in the absolute value of that number, meaning that we're not going to focus on the sign when we're talking about the strength of the relationship. That's just the direction. Sign is direction. The absolute value of the number is the strength of the relationship. If I give you two correlations, like negative 0.8 and positive 0.2, which one is stronger? Ignore the positive, negative. 0.8 is stronger than 0.2. Doesn't matter whether it's positive or negative, it's how close it is to either negative 1 or positive 1. The strength of the relationship is quantified in the absolute value of that number in your coefficient. Now that we know that information as foundational to studying correlation, I want to use correlation in hypothesis testing. Now, the reason that I'm doing this, or maybe I should say the reason why it's necessary to point this out, is because you can simply do a correlation in Excel or JASP or R or SPSS, and it will tell you whether your correlation is statistically significant. It's really simple to do. It's a very simple analysis. But what we're moving into is not just correlation, but regression. I want to move simply from having one variable related to another variable to one variable predicting another variable, and then multiple variables predicting a single outcome variable. That's going to be linear regression and multiple regression. That's going to come later. So for now, we're going to focus just on correlation, and we're going to look at the way that we could use hypothesis testing to uncover the relationship between two variables. Here is our research question. A boss was interested in the relationship between job satisfaction and burnout. He collects data from 200 mental health counselors, measuring their job satisfaction overall score and their level of burnout. Well, how can we determine whether there is a significant relationship between these two variables? Let's think first of what the relationship probably would be. Now, burnout is stress. Burnout means the job is really wearing on you. So as burnout increases, what we would expect to see is a decrease in job satisfaction. Make sense? But if things change so that your level of burnout decreases, you have a real sense of satisfaction in your job, then job satisfaction should increase. We should see a negative relationship between these two. What we have are two scale variables. So, step one, let's select the appropriate test. We're going to be using a data set called jobsatisfaction.jasp that you have downloaded, put on your desktop. So we're going to come to that in a moment, and when we do, I'll show you how to do this correlation in JASP. We're using correlation because we have two scale variables. The first variable, burnout, is going to be our independent variable. So it has to be scale level, it has to be quantitative. It's the variable that's going to go on the x-axis. The second variable is our dependent variable, that's job satisfaction. That's the one that will go on our y-axis. So now we have two scale variables, one on the x-axis, one on the y-axis. Now, does it matter which one you put on the x versus the y-axis? If it's just correlation, it doesn't matter. The correlation between burnout and job satisfaction is going to be exactly the same as the correlation between job satisfaction and burnout. There's only two variables. Their relationship is the same no matter which one you put first. However, if we're going to do hypothesis testing, then it does matter, because we're going to use one to predict the other. So now we have to think, which is the better predictor versus the outcome? Does job satisfaction tell us about your burnout, or does burnout tell us more about job satisfaction? So theoretically, we're going to say that level of burnout should predict job satisfaction. Therefore, burnout is our predictor, job satisfaction is our outcome. We're going to put our predictor on the x-axis, our outcome on the y-axis. The assumptions that we test before we do our correlation would begin with making sure that we don't have outliers. No outliers with high leverage values. There's one way to check for this, which is called case-wise diagnostics. That's something that we created with our stats software. We're looking for minimum and maximum values that exceed 3 or -3. That is really reflecting standard deviation. So more than 3 standard deviations, that's a pretty different type of value. It's an outlier. However, you will see 3.29 is a possible cutoff score. We could adjust that value. I'm just going to use 3 for simplicity. But if you have outliers, you're going to need to do one of two things. You'll either remove them or Winsorize them. Removing them is easy, but you lose data when you remove those numbers. And that's not really what we want to do. If we can preserve those values, it's going to be better. Therefore, if possible, I like to Winsorize outliers, which means that I'm going to take this number, which is extreme, and I'm just going to pull it back in line with all the other values. I'm going to keep it as the largest value, but it's going to be the next highest reasonable value in my data set. So let me illustrate that with a small data set where I have two versions of an x variable, one which has an outlier and the second which I have fixed by Winsorizing. x1 is our original predictor. You notice it has an outlier of 20. 20 is a very different number than the other values. The next highest value is 8. In x2, I have fixed the outlier by Winsorizing it. I have made it still the highest value, but it's the next highest reasonable value. I've changed it from a 20 down to a 9. Winsorization removes the leverage of that value. Let me show you why I want to do that. There's a number of problems that occur when you leave that outlier in your data set. Number one is the mean is going to be distorted in the direction of the outlier. The 20 is the highest value in our data set. So you'll notice that with the outlier, the mean is 6.44. When I Winsorize the outlier, it becomes 5.22, bringing that mean back in line with the other variables. The second thing that's going to happen is we're going to increase variability in our predictor. The standard deviation with the outlier is 5.64. When I fix the outlier by Winsorizing it, it drops the variability down to 2.82. And that's actually going to make it easier to find a correlation. It's going to strengthen the correlation as a result of moving that extraneous noise. So really there are three numbers that we're interested in with our correlation when we think about our sample versus the population. So we want to report our mean, our standard deviation, and the correlation coefficient. All three of those can be affected by the outlier. If we don't fix the outlier, then the numbers that we use from our sample to say, this is what's true in the population, those numbers are going to be biased. The outlier biases our population parameter estimates. Remember, numbers from a sample are statistics. We use the statistics from our sample to estimate the parameters in the population. We use the mean of the sample to estimate what the population mean should be. We use the mean, or we use the standard deviation of the sample to estimate what the standard deviation in the population should be. Those numbers are going to be biased. That's going to create problems, and our results are not going to be replicable. So fixing the outlier fixes that issue. Having outliers in our data set distorts the normality of the distribution. I'm going to show you a little bit more about this when I get to normality. But then there's one more that I want to tell you about, and this is one that we sometimes don't think about, but it's really important. When you're doing research, it is important, it is imperative that we protect the confidentiality of the people who are participating in the research. Outliers can compromise that. They can identify people in the data set. And this happened twice in this particular data set that I'm showing you. I had two cases. One was an individual in this data set who was in his 80s. This is someone who had been with the organization really since the beginning. He was an emeritus member of the organization. He still came into work and everyone knew who he was. Point is, if you look at this data set, you can find his responses. You just look for the age of 80, that's the guy. So that compromises his confidentiality. The second case was we had someone in this data set who was transgender. The options were male, female, transgender, and there was one person who picked that third option, meaning that you can identify exactly who that individual is in my data set as well. So what I had to do when I gave this data back to the organization was to remove those two cases so that you couldn't identify those two individuals. We want to be sure as we're making choices about our data that we're not compromising the people who are participants in the study. So I've been talking about outliers and leverage. Let me show you what leverage actually does. Let's start with a beautiful, nicely behaved data set where we have an X and Y value that have this moderate positive correlation of 0.36. There's no outliers in this data set. But if I start introducing outliers, those outliers create leverage, which means they change the relationship. If I put an outlier on the x-axis, it's down here in the lower right, the leverage pulls that regression line down flat. Now my regression equation becomes 0. The relationship disappears. That outlier is distorting the relationship, making it appear as though there is no relationship when in fact there really is. Fixing the outlier would fix that. If I have an outlier in the upper left on the y-axis, I could actually reverse the relationship. So instead of being a positive 0.36, it becomes a negative 0.09. And if that outlier is both an X and Y outlier, here we see that in the upper right corner, now I have artificially strengthened the relationship, which again is distorting the population parameter estimates. I say there's a relationship of a 0.53. No, there's a relationship of a 0.36. I have distorted or artificially strengthened that correlation because of that outlier. This is what I mean by the leverage that's created by an outlier. That line, that regression line, is a balancing point of all of the data points. Adding an outlier pulls on that regression line, like leverage, like you have a lever on a device, and it's anchoring, it is dragging it off in a direction that creates a distorted picture of the relationship between the variables. The second assumption we want to look at is normality. We want to make sure that X and Y are normally distributed. One way to do this is to remove the outliers, as we've been talking about, but a second is to check a test that we can find in JASP called the Shapiro-Wilk test. We want to make sure that that test is non-significant. If it is non-significant, then we've passed the assumption of normality. Another assumption is linearity. Is there a straight line relationship between the variables? Now this is something that really, this is the reason why we're doing correlation, to establish, is there a linear relationship? This is something we might check later on in the process. We'll just look at our scatter plot to see whether or not this relationship exists. We should see a straight line relationship, the dots around that line, as opposed to maybe something curvilinear, where it starts low and gets high and then drops off again over here. There's some kind of weird non-linear relationship between the variables. Homoscedasticity. The Y variability is the same all along the X-axis. This is also established by looking at a scatter plot. So we look at the scatter plot. If there is homoscedasticity, if the variability is the same all the way along the X-axis, we'll see those dots sort of aligned on the axis. We can just draw two lines that represent the boundaries of those dots. But if there is heteroscedasticity, if the variability is not the same all along, maybe we see a fan-shaped or a funnel-shaped cloud for our scatter plot. Or maybe we see something as bow tie-shaped. All of that would be bad news for our model, and it would have to be addressed in some manner. Probably we're not going to be able to do any kind of linear correlation with those values if this assumption of homoscedasticity has not been met. So that brings us to step 2. Let's establish the null and alternative hypothesis. The null hypothesis is going to be that our sample is drawn from a population where there is no relationship between X and Y. We learn nothing about job satisfaction from knowing burnout scores. There is no relationship. You remember when we're using samples and populations, for the sample we use an English letter, like R, and in population parameters, we use a Greek letter. So what is the Greek letter for R? It is rho. However, rho looks like a P. Therefore, when you see this null hypothesis, H sub 0 colon, you would say that is rho equals 0, or there is no correlation in the population. The alternative hypothesis, H sub 1 colon, rho does not equal 0. There is a correlation in the population. And notice we're not establishing, is that correlation going to be positive or negative? We could do that in another setting. For this example, we're just going to keep that two-tailed test idea. There is or is not a relationship. So step 3, select the criterion for statistical significance. And for this one, we're just going to keep playing the hits. Go back to the values that we have always relied upon. We're going to keep our alpha level at 0.05. Our degrees of freedom is n minus 2, where n equals the number of pairs. In our data set, we have 200 mental health counselors. That means our degrees of freedom is 198. If I want a critical value, I can look that up in a t-table. T with 198 degrees of freedom, it's going to be real close to 1.96, probably 1.97, I believe. That is how I could test between different correlations. So for this example, we'll just determine whether there is a statistically significant correlation in the population using our sample data. So we can stick with our alpha of 0.05 two-tailed test setup. Step number 4, calculate the test statistic. We can always calculate our statistics by hand, and if we did, this is what the formula looks like. And I could have you plug in numbers and calculate this, but that'd be kind of mean. Let's just use the statistics software to do the math for us. That said, however, let's look at what this formula is actually doing. It is the amount of variability together divided by the variability separately. So what we see here in our numerator is we have the sum of xy minus the individual contributions of that. So that's how much the variables are varying together. And then here's the variability of x and the variability of y. So we are removing the variability separately, or let's say getting a ratio of the variability together over the variability separately. That is how we're getting this standardized correlation coefficient. Well, now we get to actually have some fun. Let's do this correlation using JASP. So I've given you the data set. It's called jobsatisfaction.jasp. Here's how we could get this data set open so we could run the analysis. If you have JASP open and you're looking at this splash page, we could go to the main menu, Open, Computer, Desktop. On the desktop, we will find the job satisfaction data set that you downloaded. Click on that and click Open. Alternatively, you could just double click on the data set itself. Because it's a JASP data set, it will open JASP and bring you to this page right here. Let's take a look at the data. We have a lot of variables here, more than we've used previously. So let me just familiarize you with these variables. This data set is designed so that we can do not just correlation, but simple linear regression, multiple regression, hierarchical regression. We'll use this in a lot of different ways. The random ID number in this first column is just simply a number that corresponds with the cases. You notice it matches up with this first column that JASP gives us. What I'm doing here is creating a name for each case. The reason I do that is because in a real data set that hasn't been cleaned, there's probably some cases that maybe it wasn't a legitimate case of answering the items on the survey. Maybe that was just like a test. Somebody got in and clicked on a few buttons just to make sure that the survey was working, and that is not a true response. Or maybe we have some problems with multivariate outliers, somebody who's just answering one on everything across the board. I'm going to need to remove some cases most likely. By adding that random ID number, I know which case I'm talking about. So I'll run a test and it'll say, item number 126 is a problem child. Let's remove that from the data set. I'll just scroll down, find 126 and delete it. Not absolutely required, but it makes life a whole lot easier when you have random identifiers there in your data set. The variables include job satisfaction, JS, burnout, BO, turnover intention, that's your intention to leave the organization, compassion fatigue, and compassion satisfaction. Those are all scale level variables. There's other variables in here that we'll take a look at. We're only going to focus on job satisfaction and burnout for this example. So let's do our correlation. There's not a specific correlation drop-down menu because correlation is a subset of regression. Let's go to the regression drop-down, and then under classical, we will find correlation. Step number one, we'll move our two scale variables from our data set into the variables box. Move in burnout, and then move in job satisfaction. In this case, it matters which variable goes in first, because we're going to put our predictor in first, independent variable first, followed by the dependent variable, the outcome variable. The correlation would be exactly the same if you switched them. However, because we're using one to predict the other, we want to be sure that burnout is on the x-axis and job satisfaction is on the y-axis. Then for the settings, under additional options, click on Display Pairwise. You'll notice that the original correlation matrix converts to something that is much easier to interpret and understand, where we have all of this information in a single row. Let's get report significances by default, get flag significant correlations. And then down here, my favorite setting, sample size. I'll tell you why in a moment. For the plots, get the scatter plot, and I want to check the densities for variables. That's going to tell us a lot about the bivariate normality. There's one other setting. Scroll down a little bit until you find assumptions, checks, twirl open that pane, and we have a choice. We can either do multivariate normality or pairwise normality. How do you choose? In this example, you only have two variables, bivariate. So we'll use bivariate normality. If you had multiple variables, you would have multivariate normality. We can still do a Shapiro-Wilk on either setting, but we'll want to choose the one that's appropriate to the setting that we have. Although, that being said, if you run a multivariate analysis on just two variables, you'll get exactly the same output as you would if you ran the bivariate analysis. Either one of these two are going to work the same way. Now with that, I need to make a point about why I think that the sample size is my favorite setting. This goes back a few years. It was at the beginning of COVID. Everything had locked down. We were doing classes online. And I'm sitting on the back porch, hanging out, enjoying the weather, because remember it was springtime, hanging out with the dogs. We're all on the furniture out back. They're sleeping in their dog beds. We're having a good time. I'm converting all of my SPSS notes into JASP, so I could use them for this class. And as I'm doing that, I found some of the results that I would get from SPSS didn't quite match up with JASP. And one of them, which was, should have been there, was sample size. So you can see what's happening in SPSS. So I wrote to the JASP team. And the lead, Jan Wagenmakers, wrote back and said, that's a great idea. We do need sample size. So it matches up with SPSS. And it wasn't too long after the new version of JASP came out, and son of a gun, there was sample size in the correlation. So I don't know how much I had to do with that. I'll take credit for it, of course, but it's still my favorite setting because I remember sending off that request and getting a response back from them that says, we'll be sure to include that. And they did. Okay. So let's get back to our analysis. Step number 5, we're going to interpret the results and write up the findings. The first thing we're going to look at is our correlation table. Here we have the variables burnout and job satisfaction. Burnout predicting job satisfaction. There are 200 cases, and the correlation between these variables is a negative 0.650. The 3 asterisks tell us that this is not only statistically significant, it is significant at the p less than 0.001 level. And we see that reflected in the p-value. If we really wanted to know what that number was, we could go in and adjust the decimals in the preferences and stretch it out until we found out what the true probability was. For our purposes, if it's less than 0.001, that tells us everything that we need to know. When you are writing up the findings, we'll include R, that's the name of the test that we're doing. 198 is degrees of freedom. Remember, that's 200 minus 2. And our correlation is a negative 0.65. APA style recommends not including that leading 0. What we see is in the output, there's a leading 0 in front of that correlation coefficient. Now, this is just by default in most statistical software. Therefore, it ends up in a lot of publications. I always take out that leading 0. I'm a little OCD. I want it to be done just right, and so I'll remove that leading 0. You'll see me do that. It's, I wouldn't say optional, but it's what you really should do, although you will see exceptions to that in actual publications. So we have our correlation of a negative 0.65, p less than 0.001, and then the r squared of 0.423. That r squared is going to stand in for our effect size. I want to take a look at the bivariate normality. And to do this, we're going to look at multiple plots that have been overlaid. The first one, of course, is our scatter plot. Here's our scatter plot. You can see our nice negative correlation represented by that downward sloping regression line. So on this histogram for burnout, you'll see there's a positive skewness, meaning there's more cases on the lower end than on the higher end. It's slightly non-normal. I guess we should say that that is good news. It's good news at the human level. That means that there's more people with low levels of burnout than with high levels of burnout. That's good. It's not so great statistically, but it's good news for the people. However, we're going to need to account for that as we look at our bivariate normality when we do our test. Well, I'll show you the interpretation. Now, going back to our histograms, this second histogram is for job satisfaction. Here we see it's mostly normal. If you just focus on these two longest bars in the middle and then you look at the dots, you'll see, yeah, most of the dots are clustered around where those two highest bars are. Now, the same thing is true with our burnout variable. Look at that tallest bar. Most of the dots are clustered according to those histogram bars. We're seeing the same information. In the upper end of burnout and the highest level, rather down here, the lowest level of job satisfaction, you notice there are very few cases down there, and there's a lot of variability. We see greater variability in the middle of this scatter plot than we do in the extremes of the scatter plot. So this combination of scatter plot and histogram gives us a lot of good information about what's going on with our variables independently and together. The assumptions checks, we'll look at our Shapiro-Wilk test, tell us whether or not the assumption of normality has been met. We have burnout and job satisfaction, a Shapiro-Wilk value of 0.98, which we can interpret looking at our p-value. It's a 0.29. How are we going to interpret that? First, we usually interpret our assumptions tests more stringently than we do the hypothesis test. Our hypothesis test, we set the probability at 0.05. But for the assumption test, we might set that at 0.01 or even 0.001. And what's going to help us make the decision of where to set that value is the number of cases that we have in our data set. We have 200 cases. Plenty of justification for using 0.01 or even 0.001. We want the data to be really a mess before we have to start messing with transforming data sets. So we're going to keep this, we'll keep our standards high. Unless it's a real disaster, we really would rather not do transformations. So in this case, that 0.02 would be non-significant when we compare it to a cutoff score of 0.01. Because the assumptions test is non-significant, then the assumption has been met. We want to see non-significant with assumptions tests. Bivariate means only two variables. If we had multiple variables, that would be multivariate. And we can create a correlation matrix with those multiple variables. So let me just show you this in JASP. Go to our original data set, and we're going to start with a new correlation. So we'll go to regression, correlation, and this time I just want to drop in those first 5 scale variables. So I drop each of those into the variables box. The first thing that you see is the correlation matrix. And what I want you to notice is that all of the data are in the lower left side of that correlation matrix, and the upper right quadrant is empty. Well, why is that data missing? And the answer is JASP could put that information in the upper right quadrant, but it's just duplicate information. It's the same information that you have in the lower left quadrant. You don't need any other information. Everything you need is contained right here in this matrix. The reason I mention this is because when you do your assignment for this week, you're going to do multiple correlations. They'll look just like this table, this matrix, and you'll be able to determine, let's say, the correlation between turnover intention and compassion satisfaction. You just find the confluence of those two variables, and they'll give you the correlation that you're looking for. So let's go back to the analysis that we have been focusing on. Let's take a look at that scatter plot. What I like to do is resize the scatter plot so that it looks better. I just like the appearance of this with the slightly smaller dots and that downward line. The data stay exactly the same. I just like the appearance with my resizing in that way. Now, I've mentioned the effect size previously. Let me tell you a little bit more about what we're doing with effect sizes with correlation. Sometimes when we do effect sizes, we have some special formula that we have to calculate, like for a Cohen's d when we do a t-test. None of that here. This is the easiest way to calculate an effect size. All you do to get your effect size is you square your correlation coefficient. Here's our correlation coefficient between burnout and job satisfaction. It's a negative 0.65. To get the effect size, square the negative 0.65. You notice that when you square a negative, it makes it positive. That gives us a value of 0.42. That is our effect size. That is our R squared. Now, the R squared can be easily converted to a percentage. The R squared is telling us the proportion of variance in one variable that is explained by variance in the other variable. Or if we put this in terms that we have been using for our example, the effect size for burnout, R squared equals 0.42, indicated that a large portion of the variability in job satisfaction, 42%, was accounted for by the level of burnout that the counselor experienced. Notice all I have done is taken that 0.42 as a proportion, moved the decimal point 2 to the right, added a percent sign, and made it 42%. How much variability in Y can we explain? 42% of the variability in Y is explained by variability in X. That is the effect size. But there's stuff left over that just gets lumped into an other category. Let me use a slightly different example. When you look at actuarial tables, what are the leading causes of death in America? You'll probably see what heart disease is going to be near the top, cancer, COPD, which is lungs, accidents. Then as you move further and further down the list, there's going to be more rare forms of death or causes for death. And so you get into lightning strikes and bee stings and shaving accidents, and all of that is just, it's more than we need for our table. Basically, we can explain 80% of the causes of death with these first 5, and then what's left over, we're to put into an other category. It just subsumes everything else. That's equivalent to what we're doing here. With our R squared, we've explained all the variability that we can with our model. Everything that's left over goes into this other category, which is the coefficient of alienation, or 1 minus R squared. It's the proportion of variance in Y that is not explained by variance in X. Or in our example, 58% of the variability in job satisfaction was explained by factors other than the level of burnout among counselors, such as low pay, excessive paperwork, and inadequate health insurance. So the idea here would be, we haven't actually measured those other variables, but we know that those are other causes for decreased job satisfaction that are unmodeled in our example, but that if we measured them, we could also find some other contributors to job satisfaction. And our overall goal is to have the most variability explained with the fewest number of predictors. Here's how I'd write this up in APA style. A Pearson's product moment correlation coefficient was used to determine whether job-related burnout among 200 mental health counselors was related to job satisfaction. The data were first screened for outliers and linearity using a scatter plot. Both assumptions were met. Normality was assessed with a Shapiro-Wilk test, the probability greater than 0.01. Job satisfaction was strongly negatively related to burnout, with our R, under 98 degrees of freedom, is a negative 0.65, probability less than 0.001. The effect size for burnout, 0.42, indicated that 42% of the variability in job satisfaction was predicted by the level of job-related burnout. This correlation is presented in Table 1. And a scatter plot of burnout and job satisfaction is presented in Figure 1. And at this point, as you were doing your write-up, you would format the table of your correlation matrix, and then you copy and paste that scatter plot and call that Figure 1 in your write-up. All of that information together gives you the full APA style write-up. Those are the fundamentals. That's what you need to know about correlation. What we're going to now do is expand, build upon that. We now know about a relationship between variables. And when two variables are related, information about one tells us something about the other. We're going to build by going from simply relationship to prediction. When we know that there is a relationship between variables, we can use that first variable to predict the second variable. It gives us additional information that helps in making predictions. If we only have two variables, we're going to call that simple linear regression. But we can do better. We can add more variables, more predictors, and get an even better model to predict the outcome. If we're using multiple variables, we're going to call that multivariate regression. So we'll look at multiple regression, multivariate regression, simple linear regression. We're going to look at all of those examples next time. So thanks for being here, and I'll see you guys next week.